Well, I'm here in the observatory for an update. It was a couple of years ago that I took a shot of, I took a video of this. So since then, there's a new open frame 14-inch. This is an RC, is it?
Yes, distribution.
And there's a new camera on here, the ZWO. A new student over there who might not might not want to be in the video. And this is Nicholas, who he and I, well, he conceived of the idea of having this, and we kind of worked together to convince people to eventually build the whole setup. So we're here tonight. So Nicholas, what were you hoping to achieve tonight?
So tonight, actually, other than entertaining Graham for a bit, so you can catch up on things, we're also, the first thing we're going to do is we're going to take an image of Centaurus A, which is a galaxy about 8th magnitude, which you can't see, just to demonstrate some plate solving abilities. But actually our main aim tonight, it's a project that Justin is working on. He's a third year physics student, and he's working on a project which is kind of a long-term project over the next year or two, and that's to actually measure exoplanets around other stars, which is something that up until a few years ago was really the realm of big professional observatories. But in fact you can do this amateur or even small university observatories like ours. So tonight we know there's going to be a transit of a Jupiter-sized planet around a star called Ceibo, and it's going to cause a dip in brightness of about 1%, so it's not very much, but it's enough that we can actually pick it up. So we're going to drive around and monitor Ceibo. We're going to take images with our camera, about one every minute, and so we'll probably between something like 9 or 10 o'clock, and the actual transit's going to occur at 10 past 1 in the morning. So astronomy is about doing things at night time, so unfortunately you have to be up all hours of the night, and sometimes your thing you're trying to measure might do something at 2 in the morning. If you're lucky, it might be 8 o'clock at night, but that's not the way things work out. So at about 10 past 1, and it'll last for about 2 hours, this transit, and we'll see a dip in the brightness of the star, and then the planet will then leave the surface of the sun, at least it'll be in front of it, and it should go back to its normal brightness. So we've got software that, in fact, Justin and I have just been looking at, which will actually analyze all these images and produce a nice plot of the intensity of the star as a function of time, and hopefully at 10 past 1 we'll see the intensity drop and then go back up again, and then we'll declare our measurement tonight a success.
By which time I'll be asleep in bed, because I don't have to stay up for that.
Who said you can't stay up? No.
I didn't say I couldn't stay up. I just said I don't have to. There's a difference between those two.
Now, so I've done this work before. Now, knowing my luck, what will happen is that at 5 past 1, a cloud will come along and sit in front of the star. Which is
but only in front of the star.
Yeah, exactly.
It'll be a tiny little cloud.
Tiny cloud will just sit there in front of the star. So that's just.
Or you'll spend the whole night, and then you go to work up the data, and you look at it and you go, oh no,
I forgot to do
to do this.
Yes, but between now, so these projects for students, so they last through the second session, so through to the end of week 13, which is basically about the end of October. Now the other nice thing about this website that we've found, it's got this big database, and it's got various software that's been written by NASA, and I think it's Harvard University, and it's a really spectacular website that also predicts for us exactly when these...
So what's the website? Oh, that's the hard question now.
I can't remember. I can tell you shortly.
Yeah, right.
I can show you. But the website has this predictor, and it's predicting 11 of these transits between now and the end of October.
Ooh.
So tonight's the first one. We've got another 10 opportunities to get this right.
To get it wrong. So you want to give us a little bit of a tour?
In 294, and I want that to be different. So I want that to be, now let me remember, what is it now? In my book, I've written down our cameras and what our number of pixels are. Can you remember what it is, Justin?
I think the width one was 4,200 something.
4144 actually.
There you go, close enough.
Yep, 4144. And the height is 2822. So that's the number of pixels in this camera. And the other thing I have to tell it is I have to tell it what its scale is. That is, compared to the size of the image, what are the pixels and the focal length of the telescope. And the pixels are 4.63 microns in size. And the focal length of our telescope is 2850.
Ooh, big one.
There. And it's going to calculate it.
So what's the focal ratio?
It's an f8.
Right, okay.
So it's telling us that we've got 0.335 arc seconds, that's an area of the sky, an angle of the sky per pixel. That's really important for our plate solving. Alright, so that's all good. Now we're going to also cool the camera down. So we're going to we're going to cool it down to -5, because that's what we did the other day. And we're going to do it in 2 minutes. And we say quarter is on, go.
2 minutes, man.
That's probably a bit quick, but it'll just do it. So this is the camera over here.
Yep.
And in the back, it says a fan going here, and it's actually plugged into power. So some of these cameras just have a USB port. But because we are cooling the chip on this thing, it needs a lot more power. It runs 2 to 3 amps at 12 volts. So right now it's going through and it's cooling that chip down.
Around 30 watts.
Yeah, and we could cool it down to -30, but -5 seemed to work fine, because in fact the host star that we'll be looking at, which is Ceibo, is actually relatively bright. I think it's around about 7th magnitude. Something that you probably can't see in the night sky at Wollongong, but with this camera and it's reasonably sensitive, that's actually quite bright. And we don't want to have the central part of the star bleeding out and overexpose. So that would be fine, -5. Actually,
so you've got some high quality wiring here, I see.
Oh yes, mate. Isn't it? I mean, this is a piece of artistic work.
This is what us technical people call scientific wiring.
Yeah, it's the scientific. So longer term. So that's why tonight we're staying here the whole night, because I don't trust this wiring, because this thing swings around and does various things. Because it's going to have to do what's called a meridian flip at some point, which means I'm not convinced that these mightn't catch somewhere.
Yes.
And because of that,
ultimately the aim was Hull was going to be part of it, not so much now, but to get it so that this can be run remotely.
Exactly. And so what you do is you set this all up, and some of the software here allows you to run all aspects of this telescope system. You then set it to go, and you come back the next day and you pick up the data. But in order to do that, we need to have nice tidy wiring. You can see it's kind of it's research quality.
It's research quality.
But this would be much tidier, so that we'd actually be, really convinced that we could go away and leave it, and it wouldn't get itself into trouble. But in particular, this port here is of interest. Right now, we've got a little device here we can flip. This is called a flip mirror. Right now, the light's coming down to the camera.
Yep.
There's a little knob we can flip, and it actually goes out to this eyepiece, so we can actually look and hear at what we're looking at. But what we're going to do is we're going to take this eyepiece out, and we're going to
another camera in?
We're going to not put another camera in.
We're
going to put in something which is really fancy, but it's this thing here. So this is the guy here that's going to go on instead of that eyepiece. And why on earth do we want to do that is because you can see at this little hole there, what we put in there
with an SMA connector
is a fibre optic cable.
Yep.
Now, why would you want to put a fibre optic cable? Because these are like from the telecommunications industry, and this one's actually designed to work really nicely in the near infrared. The reason why we put that on is because we want to, in fact, we want to collect a spectrum. Here's a spectrometer, and we put the spectrum.
So this one is at Ocean Optics?
It's an Ocean Optics. It goes into there, and it goes out. We can just connect it to the USB port on the computer. We've got some software that will actually read a spectrum, and the spectrum of a star tells you a huge amount of information. And we want to do this because, and it's also related to our star Ceibo, is because we actually not only want to look at the intensity of Ceibo, but we want to watch its motion. And when a star moves, it actually also moves the spectrum, but a little tiny amount. And in particular, the star has a large motion, which we don't want to know about. In fact, the software takes into account the fact that, for example, the Earth's orbiting around the sun's moving around the galaxy, that actually also produces what we call a Doppler shift movement in the spectral lines. What we want to do is to in fact look at the impact of this Jovian Jupiter-sized planet going around the star. It's going to cause what's called reflex motion, so the star's going to wobble backwards and forwards like this, in fact towards us and away from us. And if this is, Doppler shift is like hearing an ambulance going past. You can hear the sound wave change in pitch. Same thing happens to light. The light frequency changes when things move. And so we can do that in principle by using a spectrometer. Not this one, because the Doppler shift we're looking for is really, really small. And so we're going to eventually use a spectrometer that we actually use, and then Graham's familiar with this, a spectrometer that we actually use for greenhouse gas measuring in the Earth's atmosphere. It's called a Fourier transform spectrometer. It still produces a spectrum, but it kind of does it with using the interference of light, and it has to do a Fourier transform to produce a spectrum. The thing about that spectrometer is, unlike this thing here, which we're not really sure about the wavelength range, and the calibration is tricky and it's a bit messy and temperature sensitive, the Fourier transform spectrometer has a resolution that's just many, many times higher than this spectrometer. Its frequency is really well calibrated because it uses with reference to a Heaney laser. And so it has a range of advantages, and we just happen to have a high resolution Fourier transform lab right beneath our feet, kind of just over.
Yeah, just over there, yeah.
And not only that, we've got the only Fourier transform spectrometers in the world, as far as we know, working in science, that are fed by fibre optics. Up till now, they've been fed in various other ways, but not by a fibre optic. And we've done this quite successfully. So I had this idea, probably in a shower or something or other, I was humming away. I suddenly thought, why not put the output from this telescope through a fibre optic into our Fourier transform spectrometers, which are far more superior to these grading spectrometers. So these are what they call dispersive instruments that the astronomy community generally uses. In fact, they've always used, and I've never understood that. And it's kind of historical reasons, in part because we've never had access to a telescope being able to feed via a fibre optic into a Fourier transform spectrometer. So we think, in fact I think, that we can do both. We can not only look at the transit, but we could also look at the Doppler shift in the spectrum together. And so we also have some special software that can actually handle both at the same time. That will be a unique measurement. He says with an evil laugh. Not really, actually.
Well,
so that's.
he says with a naively optimistic laugh.
Yeah, oh, that's the one. Yeah. I thought it sounded evil to me, but anyway.
No, I've been around this place long enough to know naivety when I see it.
Oh. So anyway, so that's where we actually want to head, and that's flapping around. I don't know where it comes from. Where it's going to.
This is science and it's coming
Yeah.
Yeah, that is scientific.
It is. It's looking at the ground, so there's obviously something came up through there.
There'll be some sort of a, I don't know, some sort of a force that is coming up from
Look,
the ground
it's still swinging. I'm breaking that.
That's the fine balance for the telescope.
Now you made me lose my train of thought, which is quite happens quite often. But anyway, the thing is that that's where we're heading to, probably in the next 6 months to a year. But we might be able to get a smaller version of these Fourier transform spectrometers actually into the building. But because these fibre optic cables, particularly for the infrared, are there's a long story about why we're going to be using them in the infrared. But they're quite expensive, unfortunately. They're probably a cable to go from here down into the room below. We're probably talking about 20 metres, and that's probably $5,000 worth of cable. So
Yeah, actually I'll go outside.
yeah.
So
I can get an idea how far down it is.
yeah, I'll see if we can do that without dropping my camera. But we're up on the roof, and just down there is, oh, you can't really see, but there's a bench down there. Yeah, you can't really see. But so the dome is right up on the roof of the building. So you can see we're reasonably high up from University. It's the highest point in the year, I think. But yes, I'll go down there later on.
Precisely.
We've had this set up for a couple of years now, and been working on it. And Nicholas was telling me that it was this a couple of days ago that he found a little tab inside of the software, because whenever this telescope drives, it's supposed to drive the dome so that this slit, this opening is in front of the telescope. But it would just get out of whack all the time. And after 2 years, he finally found a little form where you put in the dome of the telescope and a few bits and bobs. And lo and behold, it works. So, so now are we on Centaurus A?
Yeah, I just noticed talking about forms of it was set to -13, that's why it wasn't centered.
Right, so we pointed out.
Okay, now it's centered reasonably well now. So what we're going to do is we've just happened to be, we're going to pick a random, what's that, Centaurus A. It's also called the Hamburger Galaxy. I don't know whether it's chicken or it's beef, I'm not sure. It's probably veggie. But it's a
These days, any veggie.
yeah, it's a big blob of a thing, but it's got dark lanes through it, and so it kind of reminds people of two buns pushed together.
Oh, I can slot in my shot of it.
Yeah, why not?
Yeah.
So this is just to demonstrate when you can't see what you're looking for, how do you find something or other? And so in the first instance, you drive your telescope roughly to where it should be pointing. And if you're lucky,
Right, but that's all done by computer. You select it on your target list.
exactly. But often your object that you're looking for will actually be out of the field that you're looking at. You won't be able to see it. It's also, particularly a galaxy, are quite dim, and so even if you run a quick 5-second shot on your camera, you still won't see it.
And most of them are also relatively small. So.
Yeah, but this case here, so what it does is it drives to somewhere nearby, hopefully not too far away. It'll take an image, and then it does a thing called plate solving. It actually compares the star field, so it picks out about 50 stars, compares it with a database of stars. That's why we need to know the size of the image. This was pixels per arc seconds per pixel. It needs to know things about how you've taken the image. It then matches the two up and says, oh, I know where you're pointing. You're actually off, and it actually drives it to where it should be, and then it takes another image. And then in this case, we've asked it to drive to within 50 pixels of the center of the image. So it should line up fairly well. Then our image the object that we can't see, hopefully is right in the smack in the middle of our field of view. Then we can take a much longer image, say a couple of minutes, and then we should see
With your cooled camera.
with our cooled camera. And now we should see our Centaurus
All right,
A.
so let's do a plate solve.
And what will happen, of course, no pressure. If it fails,
Yeah, because we've got the high quality recording gear here and the
if it fails, it's Justin's fault.
You gotta make sure the mirror's flipped, or you won't see anything.
Yeah, make sure it's
I
flipped.
No one's ever done that before. I forgot to flip it, I'm sure.
Yeah,
I wonder who-
we could take one. We're going to turn the light out. Is that going to be a problem for you?
No,
Okay. We're also going to put it onto night vision.
actually, I've got my little dim thing over there.
I wouldn't just put dim and you in the same sentence. Surely turn on.
It's funny you say that because I'm pretty sure you have in the past.
Oh yeah, I have, haven't I? All right, so let's just see. What I'll take just one quick image, just so it's going to be 2 seconds. This is for focusing. Take one. Let's just see what happens. And if it's blank, then we know that the thing needs to be flipped. So it looks blank. There's nothing there we can see. So Justin's now going to just flip it.
Yeah,
There we go.
there.
Okay, and there we go.
It's a very technical way of making sure it's right. You just try it one way, and if it doesn't work, you try it the other.
Oh,
Oh, look at that, we've got some stars.
All right, so
Right, so there we are.
somewhere in there potentially is
Right in
Centaurus
the
A.
middle.
Centaurus A could be there.
Oh, so
or-
you haven't
or-
done plate solve yet?
No, haven't done plate solve. So it could be over here.
Right.
We don't know.
So let's have a crack.
Let's have a go at it. So let me just double check everything's good. The camera's now cooled to about -4.5, -5. That's fine. We're going to do a 20-second exposure. I think we'll actually bin that back out to 1 by 1. 20 seconds when it's finished. The plate solving, it's going to use a thing called plate solve 2.
No, plate solve as well.
Yes.
Plane solve also.
Yes. Alright, so that look, what could possibly go wrong?
Do you know, when I was saying that, it almost felt to me like you weren't listening to what I was saying.
It was in his own train.
It was that sort of response you get of, that's right.
Yes, Graham.
Yes,
Alright, so Centaurus, just making sure that's got a location. It looked like it's okay.
It's all location,
Salute to,
location,
and then
location.
centre on location. Looks all good. It's amazing how things can find, because I've probably forgotten something, but it'll, right now I just hit the go button. Run sequence.
Wish I had now.
Oh. It's going somewhere else.
Wow.
Now see the dome now follows and like the centre itself.
Yeah. It's a lovely dome. A very high quality piece of art. Those noises are meant to be there.
Mm-hmm. Don't you just like that rumble?
I do. It's a scientific rumble.
Keeps me up at night.
Well, literally.
Exactly.
Alright.
Now it's doing a search.
So, oh, it hadn't even driven to the target before.
I thought I had. That's the thing it's trying to solve.
Alright. So that's a 20-second exposure.
That's a 20% exposure. There's a few stars there, so it needs only about 50.
So this is it. It's uploading to astronomy.net now?
No, it's doing it locally.
Oh, it's doing it locally. So you've downloaded a database.
Yes. Yes, so we've got
A
about
very small database, no doubt.
500 megabytes.
Well, could have been bigger, I guess.
It could have been bigger.
So it's just a bunch of coordinates, really?
It has, I don't know how that does actually. It probably is, for every image in here, for every star, it'll tell you what its coordinate is.
Yeah, it'll have
On it.
right ascension and declination, probably. So it's still solving, is it?
They still solve it, which is not good. Normally it would have found that probably in about, I would have thought 10 seconds.
So what we're saying is probably failed first time,
Mm-hmm.
which is to be expected. You sounded so confident.
I did, didn't I? Well, the thing is, I know when I was setting...
Oh!
I know it found it.
It's having a think. Didn't move far. So is it automatically take another shot now?
It's now taking another shot.
Yes,
Got a
thank
mind
you.
of his own. It took rather longer than I was expecting.
Well, oh hello. Something's blowing out in the middle.
It's gone to, in fact, it looks to me like what I've got in there is indeed what we were
Alpha
last doing,
Centauri.
which is Alpha Centauri, because that's what we're doing last. That's why it's...
Okay, so you've got the wrong... So it's absolutely beautifully found the target that we didn't want.
Yeah. So in other words, if this was Alpha Centauri, and that's what it's done, you can see it's
So
within...
this is the case of the error between...
So what I've done, I've got Centaurus A, and I've set it up for... Oh, let's wait till it's finished. Okay, now it's finished. So I have to go back to Centaurus A, and I have to tell it I don't want to go to there. I want to go to
the target we want.
Which obviously I had forgotten to save it. And so what we do is we go to Astrobin. Astrobin, and what it has is a whole lot of things. In fact, I probably should take Astrobin Centaurus A, and it'll probably pull up. There we go, Centaurus A, Astrobin. That's right, that's what we're looking for. So I just took that photo now. Did you notice me do it?
I've got a very similar image for that up on Astrobin somewhere. That's probably better than mine.
And what I'm looking for is it's got this coordinate in here.
Yep.
So that's the header. So now I know that if I in fact copy this, it'll actually tell me exactly, that's what I want, is I say populate the link from Astrobin, and it'll actually completely change. Check.
This is
Success.
This is cheating, mate.
I know it is, isn't it? Okay, so now that's the coordinate I should have gone to before.
Let's try
because
this
I
again.
had it mixed up. I remember messing around and doing Alpha Centauri for some reason, and I overwrote it.
I mean, it's got nothing to do with the fact that I'm rabbited on while you're trying to do anything.
Oh yeah, you just distracting me.
No, it's got nothing to do with
So
that.
what I might do is I'm going to go back to Stellarium and get it to go back to... See, now it's actually on Rival Kent.
Funnily enough.
And I actually don't want it to be there.
No, you want it. So
to be...
you drove it there. That's why it moved, and we were puzzled.
I want it to be...
Alright, so, isn't that funny? It seems to be moving about to where it was before.
Go back to where I wanted it to be. Okay.
Oh, the dome didn't move far enough for the dome to move. Oh, there you go. or maybe it did. Yeah, the fact that it was... yes, that star's quite bright.
Yeah, it's a very bright star. That wasn't a galaxy.
No, the very faint galaxy that you can't see.
Yeah, was that really bright star?
Rather than that very bright star.
Okay, so now I've got that correct by having a new frame.
Alright, so here we go again.
I was wondering why it moved so fast.
One more time for the dummies.
Yeah, but the first time it did a check. It took an image and it moved a long way and I thought,
See, this is the sort of results when you get it professionally.
Yeah.
You know, it's all going to go first time, every time.
Look at that. It did it, no, I was wrong. I did it in less than 1 second.
There we go. So it's having a bit of a think.
That's what I was kind of expecting. When it took 30 seconds, I thought there's something not right here.
And you were right. That there was something not right.
Anyway, don't mix up your various targets that you're doing. So.
Well, all right. So now that looks like we saw the image change behind it. Okay. So how far is it going to go this time?
See what it's got a total error of 53 pixels. So I set it to be 50. Less than 50. So
it's going to do another little
at least
nudge.
one little nudge.
But man, that's pretty good to be within 50 pixels first. 53.
Now pixels. So that's 50 times 4.6 microns. So it's about 300 microns out. That's what we're talking about. So that's 0.3 of a millimeter. So it's pretty small error.
There we go, look at that. There was an image of Centaurus A behind there.
Oh, there it is.
There it is. There it is.
That's Centaurus A. That was just 20 seconds. So you can see that that's a not quite nice image of the hamburger galaxy that we just saw before. But that's because we haven't done a lot of things to it.
No, there's a lot of things that need to be done.
Need to be things. So we've only done it for 20 seconds. We have to do things called darks, which removes the noise from the camera. We have to do things called flats, which changes
from the vignetting.
Yeah, because there's vignetting across the field. Okay, so this one here,
frames.
you can actually see it here. There's actually always a bit darker down here and some stripes in here.
Yep.
That kind of stuff gets taken out, and also.
But for a single frame of 20 seconds.
Yeah, that's not too bad.
And there's also in the middle of that. So have you got a light pollution filter in the frame?
No, I don't.
Wow.
I haven't got one in there either. So that's pretty good, isn't it?
That is impressive.
So what I'll do is I'll run it again, but this time I won't minimize it accidentally. This time what I'll do is I'm going to, what am I looking for? Maybe, yes, there it is. I'm going to, what's already there, I have to make sure that we don't, I'm going to not make it slow. I'm going to say do not move, so it's going to stay where it is. See, what I might do also is the other thing, of course, even though this telescope tracks fairly well, we've gone to a lot of effort so that the mount is set up, and this is you probably can't see there, but it's an equatorial mount, but it's pointing very, very close to the South Celestial Pole, extremely close, so that when we turn it on and run and guiding it, the star will stay in there for probably 30 seconds to a minute, and you can see the star doesn't move very much. We could probably do it for several minutes without moving very much, but to really get a really, really nice round star over a period of say 2 or 3 minutes, we have a thing called PhD, point head dummy, guiding, and it will actually track the telescope with another little camera.
And are you using the ED80 as the guide scope?
Yes, no, I'm not using the ED80. I'm going to be using this one here, actually, up here.
So the short one? What's the focal length on that?
It's only 160.
Wow.
So
I thought you'd need something more like the 600 to track that.
Normally, but it actually works quite well.
Wow. I've always used, I've got a 2 metre focal length on one, and I always use the 80 to track.
Normally, when I get things organised, what I really want to do, if you're going to track for hours and hours and hours, is to use this 80mm telescope on this camera.
You want to pick up my little light source behind there and point it up at it?
I can actually turn the light on.
Right.
But yeah,
So we've got the ED80 is the 80mm telescope on the top.
Up on the top there.
But then we're using just this little, that's about 150 mil or something. This scope you're guiding with.
It's a 50mm and 160mm focal length.
Yeah.
So its field of view is quite large. And as a rule of thumb, what you do is you want a telescope with a focal length about a factor of 4 less than the thing that you're actually using. So this has a factor, this is the field of view, the focal length here is 2.8 meters. So we really want something that's around 600, which happens to be this telescope here, would be the best in fact to do the most accurate guiding.
Yeah.
But we haven't got it set up at the moment. So I'm going to use this one here, which doesn't do too bad a job over a few minutes.
Yeah. Well, and given you only do 1 minute exposures on the star tonight.
Exactly, it's not going to hurt at all. Let me just have this exposure. I'm going to set it up to say 2 minutes.
Yep.
2 minutes. We've got everything else going. I've turned off the plate solving, so it's not going to move.
Well, it's just going to continue to track. In other words,
to track, and we should be able to get a 2 minute
shows
shot.
PhD running in the background now.
And I haven't got it running yet because I've got sidetracked again. So I turn it on. Starshoot auto guider on a sag. I know that in fact that's that little scope there. So I go connect all, connecting camera, and then I ask it here to go begin looping, and hopefully we'll see some stars there. 2 seconds, there they are.
Yeah, so then I've got some
These little point of lights here are stars that it's going to track, and I ask it to auto select a bunch of stars. There they are. So that's our primary star in the square, but it's also going to average all these other stars together, and I say begin guiding, and we'll just watch it settle down a bit. So it's going to end up with
So there's a tracking graph down here that shows how well the head is tracking.
So it takes the first little while for it to settle down. Has a bit, so you can see the red goes up, that's the deck, and the RA is actually in a darker colour there, which you can't really see. But eventually they'll hopefully settle down around about 0 plus or minus an arc second or so.
Now the thing is that this is actually additionally, it was already tracking, the telescope was already tracking, but it was tracking naively, just no feedback, whereas this is now closing the loop.
Closing the loop, because there'll be little errors, because it won't be exactly lined up perfectly to the south celestial pole, so there'll be small errors in either of the axes, and so this one here is making it up. So now it's actually getting better and better. And you can see the error here, this is the important thing, the RMS error in pixels is actually less than an arc second, and our seeing, so how much the star flickers, is probably 1 to 2 arc seconds. So that's a second of arc is 1/3600th of a degree. So you've got degrees, you've got minutes, you've got seconds. So that gives you how tiny we're talking about in terms of an angle in the sky. Normally your seeing is the order of 2 arc seconds. That's the twinkling in the sky in a place like Wollongong. On a nice high mountain, it can get down to much, much lower than that. That's why telescopes and this professional astronomers go on mountains. But in our case, we are now tracking at about, still less than an arc second in noise, which is pretty good actually. That means that the ultimate thing is that it means the stars are all going to be held in the middle. They're not going to move very much at all. It's just actually the slight twinkling of the star that'll move around just a little bit. But otherwise we should end up with nice round stars. So now that's working. It's tracking away. And Graham will know that we actually struggled with this for quite a while.
Oh, yes we did.
And the problem with that, it turned out it was actually a software problem in the mount itself.
Oh, really?
And I upgraded the mount because we can get special,
Firmware update?
Yeah, firmware update about, when was it now? Almost a year ago, when I upgraded, all of a sudden the mount started to behave properly.
Wow.
And Before
So
that,
all the amount of frustration. you
I
went
spent a
through,
year frustrating, and the thing would never do it. It would guide, and then it would go off and do all
Just
sorts of
going crazy,
Just
yeah.
go crazy. It turned out it was actually the firmware itself had a problem, and the manufacturer never admitted it.
Wow.
Anyway,
Moving right along.
moving along. Let's now.
Yeah, I don't want my hugely popular YouTube
Let me
channel
just
to be
turn-
taken offline because of slander that you put up.
Yeah, exactly. So now I've done that. I'll just kill that. So now it's running, and it's going to run for 2 minutes. And it's got 1 minute and 49 seconds remaining, and hopefully we'll see this thing here should actually end up being brighter. We have a nice brighter galaxy. We should see more details.
But also the stars should stay round.
They should stay round.
That's the whole thing, getting those stars round. What a pain.
We could just paint them round, I suppose.
I suppose. You just go into software afterwards and post
Post them.
fix them. You can get software that you just put in there into Photoshop and things, and it'll make them round.
Isn't that how they make the Earth look round with Photoshop?
That's right. We all know it's
Yeah. I think that works as well. So I've heard that rumor.
Yeah.
Okay, so we're just
I
about.
hope we're not going into mocking mode here.
Well, actually, I don't give us our addresses because we might be able to. So
I
we're going
believe
for
that there are people out there, probably not so many in the astronomy community, who apparently hold their position very, very fervently.
Mm,
So
indeed. We must show some respect. All right, so what we'll do now is okay. We've got another 40 odd seconds.
and now at this point, Nicholas is going to dance for us to entertain.
Mm-hmm.
And the great thing about that is while he's dancing, because this floor is actually not touching the pier, you can see the light leaking up from underneath, he can dance without it shaking the telescope.
Did you enjoy my dance?
Oh, did I miss it?
You missed it. Yes.
It must have been the soft shoe shuffle.
You see-
Because I didn't hear it.
No, I was rubbing my beard.
Oh,
That's about as.
that's about as much as
That's my best dancing. You have to move your feet.
No.
Oh, okay.
It's more about the hips, I believe.
All right, so
All right.
that's done.
Done.
Okay, so there's actually a bit more detail there. So you can still see there's a bit of
That
some dark
vignette.
band. You also see, you maybe I can't see. There's actually a little round circle here, which is actually what they call a dust bunny.
Mm.
So there's actually dust on the lenses, on the mirrors, and that's what these flats do. We were talking about before. So flats is when we have this vignetting, but they also take out dust bunnies as well.
Now, do you use dithering on your between your shots?
Yes, it's on.
Yeah. So with dithering, it moves the telescope just a little between every shot. So that if you've got a systematic error that's actually in the optical train of the telescope, it moves it to a slightly different position for every shot that it takes. And it means when you stack the images, it averages those out. So dithering is another tool we use to
I
reduce
wonder,
that.
have I actually, it's a good question actually. No, I said yes. I'm not actually 100% sure.
Well,
whether
given
I
that
think-
we were just taking one frame at a
Yeah,
time.
exactly. But anyway, so that comes out. But the nice thing here is I can tell from memory that in fact that plate solve might be there. Is it the one there? Oh, there it is there. So that's the plate solve image,
Yep.
and there's the one that's now been running for 2 minutes. So you can see there's more. It's darker and there's more detail in the galaxy.
But if you took 6 hours of images of that,
Yeah.
and I used to shoot at 15 minutes.
Yeah.
My observatory's been offline for a bit.
Yeah.
We had grandchildren and that seemed to suck all my time.
Yes.
Oh, and I've got a 1936 Buick that's been chewed up a lot of my time too.
But anyway, so the
Anyway.
other thing is we don't have what Graham was talking about, a light pollution filter. We can put actually an optical filter in there that takes out a lot of the things like street lighting noise or sort of pollution and other things that come out of a city. And so that actually also pollutes the night sky. And so the night sky is a bit brighter than it should be. We can remove that light pollution. And so this actually would be even better. We'd actually take out some of that
a
background
lot
glow.
better. And if you take a 15-minute shot in Wollongong, it just gets really blown out with orange,
Mm-hmm.
which you're starting to see there.
The other thing is that notice these stars actually look to me like they're actually round.
Mm.
And the other thing is you look at this star here, this tells us, oh we can't, oh yes we can, we go plonk. Notice how like the new James Webb Telescope,
Yeah.
we've got some diffraction
Yes,
spikes.
indeed you do.
So
'Cause
that's,
you've got a,
and that's what they should be there. That's what
That's an
that's
RC.
good. That's it. It's a rich accretion. It's got a secondary mirror up the front, and it actually is blocking some of the light up the front. But then and that's what causes diffraction spikes. So we expect to see that. That's not a problem.
what I hate is when you
That's
see
round,
diffraction
round.
spikes on an image that's taken by a Schmidt-Cassegrain, which shouldn't have them, but you can add them. There's a little, I had a little set of tools in Photoshop, and one of the things you can click is add diffraction spikes,
Yeah, no, I do that.
which I never clicked.
Yeah.
Well, no, I did once for a laugh, but I never published the image.
Right, so it seems to be working fine now. So
Wow.
as you say, we will now what we're going to do is where are we? 8 o'clock. So that was just for fun.
So in the complete dark here. So where are we now, Dr. Jones?
Just testing this brightness on the screen to see if it's leaking into the telescope.
Ah, okay. So we're now actually in the part where we're taking some images of the target for the actual experiment tonight.
No, I didn't see any difference, so that's all right.
Yeah, I would have been surprised with that.
Yes, that's all right.
Beautifully made skirt.
So yes, so we've now
Catherine made,
taken.
the lovely one.
Yes, we've done 17 images now, so we've got our target star, so Graham might be able to show.
Yeah.
But this is where my finger's pointing. That's the star there. There's 1, 2, 3 stars. That's star Ceibo. That's the one that's got the Jupiter-sized planet orbiting around it. That's the one that we're looking at. And it's going to start transiting in front of that star.
Not at 110 as
Not
we
at
thought.
110, but that's actually the middle of the transit, so it's going to start an hour and a half before that, about 11:45. It just flashed, so it's taken another image. So 11:45 it'll start the transit, and so we're taking an image every minute now. So it's 10 o'clock. So that's just so we can get a baseline, so we know what the brightness of the star is before, and we'll keep on taking images right through the 3 hours of the transit, and then another hour or so on the other side, and then we'll get something like 400 1-minute images like that one there. They're about 20 megabytes each, those images, and then we're going to put this into some software called AstroImage-J, and that's going to then solve what it does. It grabs the star here and it compares its brightness with all the other stars around here, and it calculates a relative brightness, and it should be able to see if that star drops by about 1%. That's what we're expecting it to see, about a 1% drop in brightness. And
So there'll be a bit of fitting there because there's probably
Yes.
1 or 2% noise
there's about a 1% noise there, probably something like that.
with just it's the scintillation,
Just
or
the
the
natural-
sparkle of the sky,
Just
the
the
twinkle
natural,
of the sky.
exactly.
And
But-
it's, you know, you look up and you see the stars twinkle,
But that's why we want to take lots and lots of measurements.
and then
Yeah.
you have to do an average through or fill a line through those all the ones before and during and after, and then you should be able to see that 1% dip, even though the noise is around the 1%.
That's per measurement. If we have to actually sort of average some of them together, so we average the ones, so we end up having the equivalent of 2-minute integrations, and that should reduce the noise quite a bit, or even 3 minutes. We'll just have a fiddle with it to see if we can then see that. Now we know that other groups have used small telescopes to see similar sorts of effects, so we know we've got the equipment to do it.
Since we've done a video, we pulled the camera off here to try and put a light pollution filter in, and then put it back on, and it wasn't in focus, and we scratched our heads and fiddled with a pile of rings, adapter rings, and we got it back on but had to refocus.
That was a bit of a mystery.
So-
I don't understand that. Anyway,
And we've got a bit of wind outside.
well, you've got the wind, yeah.
Yes, I've got a bit of wind. But the
Yeah, we can hear that. So we're concerned the way the dome opens, we've got a flap out the front here, which is a bit like an aerofoil.
And actually it's flapping
It's
around
flapping
a
a
bit
little
now.
bit, so we have to re-engineer this so that it's a bit stronger, but I'm concerned if the wind gets above maybe 10 or 15 knots. It's just a little bit of wind there, so I'm just keeping an eye on that.
But all going well, we can go and have a hot chocolate or something.
Yeah, I think so.
And this should just keep running.
Wondering-
We've got PhD guiding the telescope, so it's running away in the background.
Yeah, this is here.
So there's our guiding.
So it's guiding on these stars, these little circle stars here. It says what 7 or 8 stars it's guiding on, and this graph here goes up to about 1, 2, and then 3 arc seconds. That's quite a small area of the sky in terms of, and then as a function of time, these little wriggling. These are the corrections it's having to make. So that's not too bad, between plus or minus 1 arc second. Occasionally it'll have this, and this here is actually the effect of a bit of a wind gust, as you can see here. Of a 3 arc second thing, but the overall error, is what's called the RMS error, is about half, 0.5, 0.6 arc second. So it's less than 1 arc second, which is pretty good actually. So what says that in fact the guiding is actually better than the actual noise caused by the scintillation of the stars. So that means we're doing pretty well. So PhD guiding is doing a good job.
So really now, all fingers crossed, this is just a waiting game now.
Indeed.
We've got a bit of, this image is stretched a bit, so the sky looks a bit clouded out. But
Yes, stretch. So in fact I put my mouse on here and I actually roll it back this way. This is actually a more reasonable thing that you'd have something like that.
yeah, so it's applying a curve to the image, but we don't need to go into that right now.
Well, I reckon the most important thing is a hot.
It's time for the hot chocolate,
Yes.
man.
Yeah,
Nobody, I brought along some nice chips, potato chips, and no one's interested in them.
I've given you some of my lollies.
Yeah,
Oh, where's your chips then?
they're just in the bag over there.
Right,
'cause
I'll
they've
rummage.
been-
I'll rummage
I
through your
might
bag.
take my bag so I can look at the cloud-free nights and maybe windy TY and just see what it's predicting for the wind.
I think that's my little thing for taking flaps. Is actually not a bad little light to have as an ambient.
Yeah. Maybe that's the thing that's getting into the camera.
All right, so we're going to go and pig out, and hopefully this is going to keep running. I was planning to publish the plots from the measurements we did the other night, but as predicted in humour, we're talking about how Nicholas was trying to make sure that everything was going to work just as it should, and it was all going to be a great success. And I made the joke about after we do the whole night's measurement, something turns up and it's, oh no. Well, as predicted, that kind of happened. So I'll go into it in another video. I haven't seen the plots yet, but apparently you can't see the transit because there's saturation on the star that we were measuring. I will go into what all that means in a follow-up video, but the guys are back in the observatory tonight. There's another transit tonight, and they are back trying again. And this time I've been informed that they've dropped it back to 10 seconds rather than a minute to avoid the saturation. I'll explain when I've got the results of tonight's measurement, assuming the cloud stays away and it's looking good, but assuming that they get a good set of data tonight, I will show the results of that. And also they've said that they'll let me have the failed image, failed workup. So when I've got both of those, I'll go through and I'll show what actually went wrong, and hopefully we'll be able to show a successful plot. But this is actually what science is. You get so many nights where it doesn't work, or well, so many experiments where it doesn't work. But I think that this experiment wasn't a failure because they now know a lot of stuff that they didn't know, or we know stuff that we didn't know before we made the measurement. A failure is when you do the whole experiment and you run through everything, you put all the time and effort into it, and at the end of it, you don't get a result, or a positive result, but not only that, you haven't learned anything. And that is what a fail is. Whereas if you do the night's work and you don't get a positive result, you don't get the result you're hoping for, but you get a result that you learn something from, that is actually a success. And probably the majority of science is the negative that you learn from, or the unsuccessful attempt that you learn something from. And at the end of many of those, you end up with one that you actually do get the positive result you're after. But that takes a lot of time, which is why it's a slow process. So I will post this up with this postscript now, and in a few days or a week, or whenever I get the second, hopefully successful plot of the transit after their measurement tonight, I'll show you them both, and I'll go through and show what went wrong and why we didn't get the result we were looking for. Okay, that's it for now. Bye.